This is the first video in a series of videos related to Unit 3, Part 1 PowerPoint Lecture Notes for CHEM100. In this series of videos, we'll be taking a look at the learning objectives listed on this slide. Please take some time to pause the video and read through the learning objectives that we will cover through this series of videos. In video 1, we are going to take a look at these three main learning objectives. We're going to take a look at the atomic theory. We're going to name, identify, and locate subatomic particles in an atom. And we're going to do a little bit of calculating the number of protons, neutrons, and electrons in an atom. First, let's take a look at atomic theory. Atomic theory is the theory that has been developed to determine how atoms behave and what atoms are. There is a previous theory called Dalton's atomic theory, which you can read more about in the reading assignment for Unit 3. And you can compare the postulates or the assumptions in this slide and those that you see for Dalton's atomic theory. So 1, all matter is composed of atoms. Atoms are the smallest unit of matter, and each atom, different elements have different atoms, right? And the atoms of every element differ from the atoms of all other elements. Chemical compounds are made up of atoms, and they are combined in specific ratios, right? And you can only have whole atoms that combine with other atoms. And this gives us our chemical formulas that we've seen before. Chemical reactions change only the way atoms are combined in compounds. So for instance, let's say you start with water molecules, right? There are 2 hydrogens and 1 oxygen atom for every water molecule. A chemical reaction causing the degradation of water will form hydrogen and oxygen atoms. And so we don't change the type and number of atoms that are involved in a chemical reaction. We only change the way that those atoms are arranged in space and within chemical compounds. So what are the components of atoms? These are called subatomic particles. The little word sub means below, right? And so these are the particles that are smaller than the atom itself. And these are called protons, neutrons, and electrons. What are the characteristics? Protons carry a positive electrical charge. Neutrons have similar mass to protons, but they are electrically neutral, meaning that they have no charge. And electrons have a really teeny tiny mass that is much, much smaller than protons or neutrons, and they carry a negative electrical charge. So what is atomic theory related to these masses and everything? If we look here, we see that there's the symbol for proton is the letter P. Symbol for a neutron is a lowercase letter n, and the symbol for an electron is a little e, lowercase e, with a superscript of a negative sign. Notice that the mass of protons and neutrons are equal up to the 100th place. So we can essentially say that they have the same mass. The mass units that are used when describing subatomic particles is called the atomic mass unit. And so protons and neutrons have essentially 1.00 atomic mass units, whereas electrons are super tiny, and we normally say that electrons do not contribute to the total mass of an atom. So the total mass of an atom is related to the number of protons and the number of protons and neutrons, and not electrons. Notice here that although an electron has a really small mass, it carries a full negative charge, whereas protons carry a full positive charge. In terms of where these subatomic particles are found, protons and neutrons are packaged really closely together in the nucleus of an atom. So protons and neutrons are packaged really closely together in a dense core, and we call that the nucleus. So protons and neutrons are found in the nucleus of atoms, whereas electrons are going to be found in this three-dimensional space surrounding the nucleus. So protons and neutrons are in the nucleus, whereas electrons are found in surrounding the nucleus. Considering the size of these subatomic particles, let's imagine that the atom was this entire stadium. A P in the middle of the stadium would represent the nucleus, which would house all the protons, all of the neutrons, and let's say little gnats flying around in this whole entire space would represent the electrons. So the most of the space of an atom is filled with empty space, and electrons are moving very rapidly surrounding the nucleus in a defined location, which you will learn about in taking a look at the Unit 3, Part 2 content. The way that electrons and actually remain as a part of the atom is due to the electrical charges of those electrons. We know that things that have similar charge are going to repel each other. So two electrons will repel each other. The same is true for two protons. They will also repel each other. However, protons and electrons attract one another. So you may think, well, how do protons get stuck together in the nucleus? It's the neutrons that are situated between the protons that prevents those protons within the nucleus from repelling each other. However, the protons in the nucleus and the electrons surrounding the nucleus now are attracted to one another because we have that positive and negative. So the electrons are attracted to the protons, and the more protons we have in the nucleus, we're going to increase the number of electrons, and that attraction is going to get stronger and stronger, and those electrons will move closer and closer to the nucleus, the more protons and electrons we have in our atom. So let's break it down a little bit more. We have a number of symbols that are related to the number of protons and the mass number. We'll see in the next few slides something that looks like this. And the letter A represents the number of protons of a given element. And all atoms of the same element are going to have the same number of protons. We can also say that if this is a neutral atom, meaning that there's no charge associated with this atom, the number of protons is also going to equal the number of electrons. And that's going to be important for helping us to identify elements based on given information. The mass number now is simply the mass or the sum of the number of protons and the number of neutrons in an atom. So we can say A is equal to the number of neutrons plus the number of protons. And we can say that Z is equal to the number of electrons, which is also equal to the number of protons. All right, and that little hash mark, we're going to say that equals number if you've never seen it written that way. So how can we find the atomic number or the number of protons of an atom on a periodic table? When you're looking at the periodic table, you will see these boxes, and within these boxes, you will see a symbol, which represents the symbol is the symbol of the name of the element. And we talked about this in Unit 2, where we have capital letter and capital and lowercase letter symbols for atoms. So there's also going to be a number, a whole number that's associated with each one of these boxes on the periodic table. And that number is the atomic number. And we also mentioned that the atomic number is the number of protons, right? So in a lithium atom, we see that we have 1, 2, 3 protons. And also, because this is a neutral atom, we have 1, 2, 3 electrons. The same goes for this carbon atom, where we have 1, 2, 3, 4, 5, 6 protons and 1, 2, 3, 4, 5, 6 electrons. So you can use the periodic table to determine the number of protons by the atomic number and the number of electrons in a neutral atom also by the atomic number. So just to reiterate, neutral atoms are those that have no net charge, meaning that the atomic number, or Z, is also going to be equal to the number of electrons in that atom. This also means that the number of charged protons equals the number of charged electrons, and they cancel each other out. So if I have 6 electrons and 6 protons, right, 6 negatively charged particles and 6 positively charged particles, when we put them together, they cancel each other out, so there's essentially no charge. Again, here we have our atomic symbol, and we can call these isotopic symbols or atomic symbols. And here the X represents the element, the symbol that you see on the periodic table, the mass number, which is, remember, the number of protons and neutrons, which represents the letter A, and Z, which represents the number of protons or the atomic number. And remember, for neutral atoms, the atomic number is same as the number of electrons. Let's do a little bit of practice. Pause the video to see if you can answer these questions on your own, and let's come back to answer them when you're ready. Are you ready? All right. How many neutrons are there in the nucleus of a bromine atom that has a mass number of 80? So we're given a little bit of information. We're given the mass number, which is 80. Right? So A is equal to 80. And we want to know how many neutrons. So first, let's find bromine on the periodic table. Bromine has, we see the name bromine here, and it has the symbol of Br. And so notice that this number above the Br, that is the atomic number. So we know that the atomic number, or Z, is equal to 35. And we also know that A is equal to the number of neutrons plus the number of protons. So we can find the number of neutrons by subtracting 35 from 80. So 80 minus 35 is going to be equal to 45. And so there are 45 neutrons in an atom of bromine that has a mass number of 80. Let us now identify the following elements. We're given our mass number, which is 186 for our first element, and the number of neutrons. How do we figure out the identity? Well, again, remember, A is equal to the number of neutrons plus the number of protons. So we can figure out the number of protons by subtracting the number of neutrons from our mass number. So for A, we can say that our number of protons is going to be equal to 186 minus 111. What we get from this is 75. So when we look on our periodic table, we look for the number 75, we end up here with the element rhenium. So we are going to write the symbol as for Re. For letter B, we're given our A value is 59 and we have 21 neutrons. So to figure out the number of protons to help us identify an atom from this element would be 59 minus 21. And when we take a look at 59 minus 21, we get a value of 38. So let's look on our periodic table. We're looking for number 38, and we end up here with strontium. So this represents an atom of strontium. Let's take a look at letter C. We have an A, or a mass number, of 127, and we have 75 neutrons. So, 127 minus 75 equals 52. So looking on our periodic table, we find number 52, and we see that represents tellurium. So that is Te for tellurium. Let's do a little bit more practice. Pause the video answer this question and come back to see if you get the right answer. Are you ready for the answer? All right. So this question says, identify the element X in the symbol, in this symbol here, where we have a superscript of 194 and a subscript of 78. We also need to give its atomic number, its mass number, the number of protons, the number of electrons, and the number of neutrons. All right, let's break it down to take a look at what we're looking at here. Remember, the top number is the mass number, which is equal to the neutrons plus the protons, whereas the bottom number is the atomic number. So if we look at this atom, the atomic number is equal to what? 78. That atomic number gives us the identity of our element, which we have here is platinum. 78 is our atomic number, and our mass number is 194. We know that the atomic number is also equal to the number of protons. So we have 78 protons. We also know that the atomic number for a neutral atom is also going to be 78, which also gives us the number of electrons. So the number of electrons is also 78. The last thing that we need to figure out is the number of neutrons. So remember, our mass number is equal to the number of neutrons plus the number of protons. And if I want to figure out the number of neutrons, then I would take the mass number and subtract the number of protons. So 194 minus 78 gives us the value of 116. So there are 116 neutrons